Greetings, fellow learners. In this video, we are going to take a look at the whats, the whys, and hows of Hopfield Networks. It's going to be fun, so let's get to it. So this here is a biological neuron, and it has many capabilities, one of the most important of which is logic. Now, if we were to connect these neurons as they are in our brain, we notice that certain properties emerge, such as memory. And this capability of memory wasn't there for just a single neuron. And so, John Hopfield in 1981, who was a physicist, posited this question: can such emergent properties arise by connecting individual computation units? And what he meant by this was that, let's say, instead of a biological neuron, we take an artificial neuron. This is specifically the McCulloch-Pitts neuron, which has some inputs, some weights, and an output. And this output is going to be thresholded by a binary threshold value, where it'll fire if it's above some threshold, and it will not fire if the sum of products is below a certain threshold. And if we were to connect multiple biological neurons like this, we can kind of represent that through a computation model that looks like an interconnection of neurons that kind of look like this. And the question that Hopfield is trying to ask is this artificial network now capable of memory? So is it capable of storing and recalling memory? And this here is a Hopfield network. So a Hopfield network is a network of artificial neurons that can demonstrate emergent properties such as storing and recalling memory, error correction, and other capabilities. And in this video, we are going to mostly focus on the emergent property of storing and recalling memory. So let's get a little bit of a high-level understanding of how these two processes work. So how is memory stored? Now, when we consider an interconnection of neurons like this, storing memory is essentially learning itself. And so learning or memory is going to be encoded in the synaptic connections between these neurons. And this kind of goes into the Hebbian theory of learning. Now, when a memory is stored, there are continuous associations that are formed. And these associations are formed with information that is known prior and other information that might be currently perceived. And these associations are also then stored in the synapses. So the synapses are continuously updating. Now, how is memory recalled? Well, memory is recalled when neurons fire in a specific pattern. And this can happen because of some stimulus. So, for example, this could be the pattern of neurons firing that correspond to the memory of eating ice cream last week when asked a question about your favorite dessert. So, when you are prompted with some initial hint of eating your favorite dessert, we are able to then recall the memory of eating ice cream last week, all because an association was created between them. Now, let's create a computation model of these two processes of storing and recalling memory. So now let's construct this computation model. It just means that this is going to be a network which is going to be comprised of a bunch of calculations. So in order to quantify everything, we have each of these, like we mentioned before, are going to be artificial neurons, like the McCulloch-Pitts neuron with a binary threshold unit. And each of them can thus take a state of either 0 when the neuron does not fire, or 1 if there is an action potential and the neuron fires. Now, these edge weights are going to represent synaptic connections, and each of them is going to have a weight that corresponds to the strength of the synapse. Higher a positive value, stronger the connection. Lower the value, then the weaker connection. And this goes in accordance to Hebbian learning, where neurons that fire together will wire together. Now, the overall state of this entire Hopfield network can thus be represented by 6 values: 1, 0, 1, 1, 0, 0, which is basically the states of the individual neurons themselves. So the goal now for us is that this network should represent the 2 memory processes in the brain, that is, storing information and recalling information. Question 1, how to store a new memory in this network? Well, let's assume that we have this Hopfield network over here, where it has certain synaptic weights, as shown in gray here. And this current state is 1, 1, 1, 0, 0, 1. This corresponds to a memory that we want to store. And so what that means is that we want to somehow encode this information, 1, 1, 1, 0, 0, 1, into the synaptic weights itself. So given the state, we want to update these weights. So how do we do this? Again, this here is going to be a computation model, so everything is going to require calculations. And so Tij is going to be a synaptic connection weight, and it's going to be the sum of all previous states plus this formulation, where Vi is going to be one neuron here, and Vj is going to be the corresponding other neuron for this synaptic connection. And so Vi and Vj, we know that they can only take 2 values, 1 and 0. And while this looks like a very intimidating mathematical expression, let's say that we apply the example right here. Essentially, it's just going to add 1 for the cases where the synapses is between neurons that are firing together or not firing at all together. And it's going to add -1 to the synaptic connections where the neurons are firing apart. That is, one of them is firing and another is not, like in this case. And so we just simply add these new weights to the existing weights and update them as such. Now, the next question, how do we recall a memory in this network? So that means given the synaptic connections that we see here in gray, we need to determine the state which corresponds to the memory that we originally stored. Remember, the state is going to be the set of all of these activation values to contribute to an activation pattern in the brain that we saw previously. And so in order to do this, John Hopfield basically made use of the second law of thermodynamics in the sense that the free energy of a closed system should decrease over time. This is a restatement of that second law of thermodynamics. And so what this means is that a stable state would be at this free energy minimum. Now, there's quite a lot of terms here, but just to be very clear of how this physics is going to be related to this computation model that we are creating, when we talk about a closed physical system, in this case, we're going to talk about the Hopfield network, which represents the interconnection of neurons in our brain. And when we talk about free energy, well, we can determine the energy of this Hopfield network using this formulation over here. It looks pretty intimidating, but it's actually very easy in principle. The free energy of this Hopfield network is going to be the sum of synaptic connections between 2 firing neurons. So let's just take 2 examples just to illustrate what's going on and how to compute total energy. So in this Hopfield network over here, we have 2 firing neurons here. Synaptic connection is 0.75. And I think that's the only one that we see here. And so the total energy is going to be -0.5 times 0.75, which is -0.375. That is the total energy of this Hopfield network. In example 2 over here, in this Hopfield network, well, let's take all of the synaptic weights that correspond to 2 firing neurons. That's 1 minus 1.5 minus 2. and this is minus 2.5. So applying it to our formulation, the total energy or total free energy of this Hopfield network is going to be negative half times negative 2.5, which is 1.25. Now, the goal in our Hopfield network is to come to a stable state that corresponds to lower free energy. So in this case, we would like this lower free energy than it is compared to this state. So in order to illustrate this energy versus state visually, we can look at the energy landscape of a Hopfield network. Now, this is going to be a lot easier with an example, which we will show later. So in this energy landscape, it's a plot of the free energy on the y-axis that we just discussed, and the state on the x-axis, which is going to be the set of all neuron states at a given snapshot of time. So what's important to note is that at these energy minimums over here, these are stable states, and these energy minimums are going to correspond to actual memories that were stored. And so the idea here is that we'll start at a random state somewhere up here, and through some updating mechanism of gradually decreasing energy, we should be able to come to an energy minimum here and hence recall a memory. Now, let's actually work through this example here, where we are given synaptic connections and we need to determine the state which corresponds to a memory. Remember, the memory that we stored was 1, 1, 1, 0, 0, 1. And we want to see if we can recall that memory, given that we are using now the same synaptic connections that should have absorbed that information. So this here now is the initial state, where it's not quite right compared to the actual 1, 1, 1, 0, 0, 1, but let's see if we can get to that state eventually. So from this state, we want to minimize the total energy. Now, this current initial state, the energy is 1.25. So in time step 1, what we're going to do now is just choose a random neuron. And let's say that we chose this one. Now for this neuron, we will take the synaptic connection and multiply it by whether the neuron is firing or not, and see if it is above 0. So in this case, 1 times 1 plus 1 times minus 2 plus 1.5 times 0, that's going to be negative 1, and it's less than 0. And so what we do is that the new state of this neuron is going to be 0. And by doing so, we'll see that the energy has decreased from 1.25 to 0.75. So we're actually stepping in the right direction. Now in the next time step, we repeat the process, select a random neuron. Now the total input to this is 0 times 0.75 plus 0 times negative 1, which is 0. So there's going to be no change here, and the energy remains the same. In time step 3, we'll choose a random neuron. Let's say it's this neuron here. And the total input is going to be 1 times negative 1.5 plus 0 times negative 2 plus 0 times 0.75, which is going to be negative 1.5, and it's less than 0, which means the neuron does not fire. So the new state is 0. And then the total energy now, well, there's no two positive, active neurons that are synaptically connected to each other. And so the total energy of this network is 0, which is still good because it's continuously decreasing. Now in time step 4 here, let's say that we chose this neuron. And here, the neuron is going to have an activation of 0. And hence, there's going to be no change in the state. No change in the state means no change in the energy. Now in time step 5, let's say we randomly chose this neuron here again. Now the total input is going to be 1 times 1 plus 0 times negative 2 plus 1.5 times 0, and it's going to be 1, which is greater than 0. So now this neuron turns into a state of 1, and the energy is negative half times 1, which is negative 0.5. Once again, the energy is decreasing. Now in time step 6, let's say that we chose randomly this neuron over here. The total input is going to be 1 times 1.5 plus 1 times 0.75 plus 0 times 0, which is 2.25. It's greater than 0. And so we're going to see that the new state of this is 1 because it's greater than 0. And the new energy, the total energy, is going to be negative 1.625. Now, this is very interesting because what you notice over here now is 1, 1, 1, 0, 0, 1. This corresponds to the state of the original memory that we had stored. And what this also corresponds to is this energy here is minimized. We actually cannot change any of these neurons to get a lower energy. And so we have empirically shown that at this energy minimum, we have recalled a memory. So what this looks like in our energy landscape here is that in the first state, initially, we had like 1.25 with this state of neurons here. And as we went forward, we could see that the energy was decreasing over the time steps until eventually we came to 1, 1, 1, 0, 0, 1, which corresponded to our memory. And this was the energy minimum. Now that we looked at this entire Hopfield network, well, there are some pros and cons here. So a pro here is that it's a really simple procedure to determine emergent properties. In this case, we looked at storing and recalling memory or associative memory that we see in humans. It can also be used in error correction or in recovering from corrupt input data, which can also find its uses in content addressable memory. The cons, however, are that we could potentially be stuck at a local minima. So let's say that we have this energy landscape over here for a given Hopfield network, and the actual memory that we want to recall is somewhere over here, in this state right here. And let's say that we start at this state here, but we monotonically continuously decrease the amount of energy we have. So we might only end up in this state, and we can't really traverse this part of the curve because we can only decrease energy, and any updates in state will stop here. So instead, in this case, if we were to have stored this memory and we start here, we might be only able to recall some false memory. So this is wrong. This, however, could be resolved through something called simulated annealing, where we introduce some temperature concept. And so even if we were at this state, we can kind of traverse this little peak here in order to get to this global energy minimum, which corresponds to a real memory. Now, another con here is the limited capacity of Hopfield networks. If there are n neurons that are connected in this Hopfield network, it can really only store 0.14 memories. So for a 6 neuron Hopfield network, it could realistically only store 1 memory correctly without, falling into the trap of recalling false memories. Now, there have been methods to overcome this, such as unlearning or using more complex synaptic connections, and also other learning procedures that come in the future, such as backpropagation. Quiz time. Have you been paying attention? Let's quiz you to find out. A Hopfield network, A, is a computation model of associative memory. B, tends towards decreasing total free energy. C, has a recall procedure based on thermodynamics. Or D, none of the above. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct options are A, B, and C. But can you tell me why? Please give your reasoning in the comments below, and let's have a discussion. And if you like this video, please do consider giving this video a like, because it will help me out a lot. Now that's going to do it for quiz time and this video, but before we go, let's generate a summary. So in this video, we took a look at a Hopfield network, which is a computation model or a network of artificial neurons that demonstrates emergent properties such as storing and recalling memory, error correction, and more. with an emphasis on associative memory, or the ability to store and recall memory. And so we took a look at how this computation model can update its synaptic connections given a memory state. And we also saw how to recover this memory from a randomized initial state. And then we corresponded this to the energy landscape, which corresponds to determining a memory here. And then we elucidated some pros and cons of Hopfield networks. And that's all I have for you today. Now, some more supplemental resources are going to be in the description below, and I highly encourage you check them out for a further understanding of the field. This is a great topic that transcends how artificial intelligence can go towards physics, neuroscience, and mathematics and computation all in one go. And it was a recipient, and well-deserved so, of the Nobel Prize. So I hope you like this video. Please do consider giving this video a like, and do check out this video to continue your AI journey. And I'll see you in the next one. Bye-bye.